As scientists study these differences, they gain valuable clues about how the early planets moved and how the architecture of the solar system evolved into its present form. The more researchers analyze Trojan families, the more they realize these clusters of objects behave like miniature versions of the asteroid belt. They contain their own subgroups, their own pairs of objects that appear to be ancient siblings, and their own isolated members that seem to be wanderers. Collisions among Trojans are rare, but not impossible. Evidence of these collisions can be inferred when clusters share similar compositions or display signs that they split from a parent body in the distant past. In some cases, two Trojans have nearly identical orbits and reflectivity patterns, leading scientists to believe they were once part of the same object before a violent impact tore them apart. Such discoveries turn these remote rocks into historical archives of celestial violence, preserving stories of fragmentation, impact, and survival through billions of years of motion. Perhaps the most fascinating aspect of Trojan Worlds lies in their duality. Every giant planet with Trojans possesses two main camps of these objects. One group leads the planet in its orbit, and the other trails behind. These two camps can be thought of as two cosmic tribes traveling in opposite directions along the same journey. They remain eternally separated by 60 degrees from the planet they accompany. This configuration gives them remarkable stability, but also raises questions about how the distribution became so uneven. In the case of Jupiter, for example, one camp contains significantly more objects than the other. This asymmetry remains one of the enduring mysteries of Trojan populations. Some models suggest that subtle gravitational tugs from Saturn could have influenced this imbalance. Others propose that the distribution reflects the way these objects were captured during the solar system's earliest days. Whatever the reason, the lopsided nature of Trojan camps adds another layer of complexity to their already mysterious existence. When researchers turn their attention to Earth's Trojans, the intrigue grows even deeper. Earth is not known for hosting large populations of these companions. In fact, for many decades, it was believed that Earth had no Trojan companions at all. The glare of the sun makes the regions where Earth Trojans would reside extremely difficult to observe. This caused a long silence in scientific literature, an absence of data that many assumed indicated an absence of objects. But the silence was eventually broken. A small but stable Earth Trojan was discovered and its orbit confirmed. Though tiny compared to the immense populations found around Jupiter, the existence of even a single Earth Trojan changed the narrative completely. It proved that Earth does indeed have gravitational niches capable of hosting such objects, and that these regions may still hide additional companions that have not yet been detected. This discovery inspired an entirely new direction in scientific inquiry. Earth Trojans may serve as valuable waypoints for future space exploration. Because they share Earth's orbit and remain relatively close to our planet, they could potentially serve as stepping stones for missions venturing farther into the solar system. Establishing a spacecraft in one of these positions might require less energy than traveling to more distant objects. Moreover, if additional Earth Trojans are found, their compositions could help scientists determine whether they formed near Earth or were captured during the chaotic early era when planets migrated across the solar system. If they are captured objects, they may contain materials that contrast sharply with typical near-Earth asteroids, offering rare opportunities to obtain pristine samples from remote regions of the solar system without sending spacecraft on extremely long journeys. Beyond the physical science, Trojan Worlds encourage us to think about the solar system in a more dynamic and interconnected way. They reveal that our cosmic neighborhood is not composed merely of planets circling the sun independently, but of a vast network of gravitational partnerships, ancient exchanges, and delicate equilibria. These small bodies demonstrate that stability is achieved not just through mass or orbital distance, but through a careful dance of forces that exist at the intersections of multiple gravitational spheres. By studying Trojans, we gain a deeper understanding of the delicate balance that maintains the order of the solar system. In them we see that the planets are not solitary wanderers, but participants in a larger and more intricate cosmic choreography. The more scientists observe Trojan worlds, the more intriguing questions arise. Are there Trojans that harbor water, ice, hidden beneath dark carbon-rich surfaces? Could some of them be remnants of early dwarf planets that were shattered during violent collisions? Might their internal structures reveal gradients of temperature and pressure from epochs before planetary formation stabilized? Every new piece of information deepens the mystery instead of simplifying it. Trojan worlds operate at the crossroads of solar system evolution, planetary migration, and primordial chemistry, making them central characters in the story of how our cosmic home came to be. The story of Trojan worlds becomes even more fascinating when we begin to look at how scientists actually attempt to track the subtle gravitational dialogue that takes place between these asteroids and the planets they follow. It is not enough to know that they exist in the Lagrange points, because these regions are not static chairs placed in the solar system. They are instead dynamic gravitational balances that depend on the constant movement and mass distribution of the Sun and the planets. This means Trojan asteroids are never perfectly still. They oscillate, drift slightly forward or backward, and perform long looping motions that could take centuries or even millennia to complete. These slow dances are not random, but are the direct result of the delicate gravitational agreement responsible for allowing them to exist in the first place. Scientists simulate these orbits on computers that must calculate millions of small gravitational tugs. Every planet, every moon, and even some large asteroids influence the Trojans. A Trojan world might be hundreds of millions of kilometers from Jupiter or Earth, yet it still feels the nudges caused by the rest of the solar system. Over long timescales, these nudges accumulate and slightly shift the asteroid's orbital path, sometimes making it more stable and sometimes gradually pushing it out of the Lagrange zone. This means a Trojan asteroid may not remain a Trojan forever. Some will eventually drift out and become independent wanderers of the inner solar system. Others might be captured anew, slipping into resonance with a planet and becoming a fresh addition to the Trojan family. One of the grand questions is how long Trojans can remain where they are. Jupiter's Trojans are ancient and may have been stable residents for billions of years. Earth's Trojans are believed to be younger or at least less stable because the Lagrange points associated with Earth are more easily disturbed by the gravitational influence of Venus and Mars. Even small shifts caused by the Moon can play a role. This instability does not make them disappear instantly, but means that Earth Trojans may come and go across geological timescales. Knowing this opens a window into the past, because every Trojan population retains a memory of the environment it was born into. If we study their composition and understand their orbital evolution, we can reconstruct the messy, early years of the solar system. Another essential element to understanding Trojan worlds is the role of planetary migration. In the early solar system, the giant planets did not always orbit where they do today. They moved as they interacted with the disk of gas and dust, and as they gravitationally pushed each other into new positions. This migration likely scattered countless small bodies across the solar system, and in the process created reservoirs where asteroids could accumulate. The Trojan regions of Jupiter might have been seeded by objects originally from far deeper in the solar system. If that is true, these asteroids are fossils from a different cosmic neighborhood. They may contain chemical fingerprints that do not match typical objects from the asteroid belt. Finding such differences would provide direct evidence that the early planets reshaped the architecture of the solar system through dramatic migrations. In more recent times, Trojans have gained attention for a different reason. Their unique orbits make them attractive targets for space missions. Visiting a Trojan asteroid requires different planning than typical asteroid missions because the spacecraft must travel to the gravitationally stable zones ahead or behind a planet. These locations are not simply along the planet's orbit, but require carefully designed transfers. Such missions are scientifically rich because Trojan asteroids may contain mixtures of rock, metal, and ices that represent various regions of the early solar system. They also may have never been heated significantly, meaning their internal structures are pristine records of the solar nebula. Studying them directly could reveal information that is difficult or impossible to learn from meteorites that fall to Earth. NASA's interest in Trojan asteroids has grown significantly because these bodies represent an untouched archive older than the planets themselves. Some Trojan rocks could predate the final formation of the Sun or may contain unaltered materials from the cloud of gas and dust that eventually collapsed to form the solar system. This possibility excites planetary scientists because it offers the chance to examine matter that has remained sealed in deep time for more than 4.5 billion years. Trojans could answer questions about the distribution of water and carbon in the early solar system, two ingredients essential for life. If these asteroids contain significant amounts of organic compounds, they may provide clues about whether the seeds of life were widespread or rare. Beyond the scientific value, Trojans have sparked interest from engineers and future mission planners because they represent potential stepping stones for human exploration. Their stable orbits reduce certain navigational risks, and their predictable positions make them appealing candidates for future resource extraction. Some may contain useful metals or water ice that could be converted into fuel. Even if resource mining is still far in the future, understanding the geological nature of these objects is critical for determining which ones might be practical targets. In a long-term vision of human expansion through the solar system, Trojan Worlds could eventually host robotic stations or serve as bases for scientific operations far from Earth. There's also a philosophical dimension to Trojan Worlds because they challenge our intuitive perception of what it means to share an orbit. Most people imagine a planet orbiting the Sun alone, accompanied only by its moons. But Trojans show that an orbit is not a private pathway. It is instead a gravitational highway where other travelers can accompany the planet in stable formations. In a poetic sense, these asteroids are companions to the planets, guardians of ancient stories, and relics of cosmic processes that shaped everything from Earth to the distant reaches of the Kuiper Belt. Their presence reminds us that the solar system is not static, but is an intricate and dynamic ballet. As we expand our search for new Trojan populations around other planets, and perhaps around exoplanets, there is potential to discover entire families of worlds that share orbits in distant solar systems. If Trojans exist around planets in other star systems, they may provide indirect evidence of planetary formation processes similar to our own. In some cases, they may even be detectable through the slight dimming they cause when passing in front of their parent stars. This could help astronomers infer the presence of planets that otherwise remain hidden. In this way, the study of Trojan worlds extends beyond our solar system and could become an important tool in the search for exoplanets. The long-term study of Trojan asteroids may also help us understand how frequently these objects contribute to impact events on Earth. Although Trojans are generally stable, it is possible for some to be nudged out of their positions and enter Earth-crossing orbits. While this is rare, it is not impossible. Studying their orbital evolution gives scientists valuable insight into future risks and helps refine our models for potential impacts. Fortunately, most Trojans are unlikely to pose any threat in the near future. However, understanding them provides a more complete picture of the dynamical environment around Earth's orbit. As we reach the final stretch of our journey through the strange and silent realms of Trojan worlds, the story of these orbit-sharing bodies becomes more than a simple scientific curiosity. It becomes a reminder that our solar system is not a static and predictable machine, but a living landscape filled with subtle interactions, ancient leftovers from cosmic collisions, and vast archives of time waiting to be decoded. Trojan asteroids show us how gravity allows for a kind of cosmic companionship, where worlds can share the same orbit without crashing into one another. It is an elegant dance choreographed by forces far older and more precise than anything humanity has ever built. The deeper scientists look into these objects, the clearer it becomes that they hold clues to origins we still do not fully grasp. They might be fragments of the early solar nebula. They might be captured wanderers that once drifted freely in interstellar darkness. They might be pieces of planetary embryos that were shattered long before Earth ever cooled. Each of these interpretations carries profound implications for our understanding of how planets form, how solar systems evolve, and how rare or common worlds like ours might be in the universe. The mystery remains vast, but the pieces fit together slowly as new missions and telescopes refine what we know. NASA's Lucy mission has become an important milestone in this search. By visiting a diverse set of Trojan asteroids belonging to both the leading and trailing swarms of Jupiter, Lucy's close-range observations will finally reveal what these distant companions truly look like. It will examine their surfaces, their bulk structure, their density, and their composition in ways that no telescope on Earth or in orbit can achieve. When those first images and measurements arrive, they will likely challenge many assumptions, just as early space missions shattered expectations about asteroids, comets, and the outer planets. Lucy's findings will shape future missions, and perhaps even inspire sample return missions that bring pieces of these frozen archives back to Earth for laboratory study. Yet the Trojan asteroids of Jupiter are not the only ones of interest. Earth has its own Trojans, including the gently orbiting object known as 2010 TK-7 and other candidates still being identified. These companions are faint, hidden from easy view by the glare of the sun, but they follow Earth in a delicate gravitational equilibrium. Their presence raises new questions. How long have they been there? Where did they come from? Are they stable enough to remain with us for millions of years? Or are they temporary visitors caught in our orbit for only a cosmic moment before drifting away again? Answers to these questions could help us understand whether other planets also share their orbits with long-lost companions we have yet to detect. Mars has Trojans as well, including the fascinating asteroid Eureka, which shows spectral hints of material once belonging to the Martian crust itself. Neptune possesses enormous Trojan swarms, possibly rivaling or exceeding the population of the main asteroid belt. Even Venus and Uranus may host Trojans, though evidence is still limited. This widespread phenomenon shows that the solar system, despite its great distances and massive gravitational forces, is capable of balancing many celestial bodies in shared orbital relationships that remain surprisingly stable over vast spans of time. One of the most intriguing possibilities raised by researchers is that Trojan asteroids could contain material from worlds that no longer exist. In the early solar system, the region between Mars and Jupiter may have once harbored a large developing planet that was prevented from forming by Jupiter's gravitational influence. Violent collisions between planetary embryos were common. If fragments from those catastrophic impacts were ejected into stable Trojan points around giant planets, then the Trojans we see today might include pieces of long-vanished worlds. This concept turns each Trojan into a time capsule that could preserve minerals and isotopes found nowhere else. Beyond scientific curiosity, Trojan asteroids may also play a practical role in humanity's future. Their stability and predictable orbits make them attractive targets for resource exploration. Some may contain water-locked-in minerals, metals that could support construction in space, or other materials that would be difficult to obtain from Earth. While resource extraction is still far in the future, early studies suggest that the Trojans may someday become stepping stones for deeper exploration, or even the raw material for off-world construction and manufacturing. By learning their compositions, humanity prepares for potential opportunities that may arise as space industries develop. The Trojans also challenge how we think about planetary orbits. When most people imagine planets moving around the sun, they picture each world traveling alone along its path. But the presence of these co-orbiting bodies reveals that planetary orbits are more like wide gravitational pathways that multiple objects can share. This increases the number of possible configurations in other star systems. When astronomers study exoplanets in distant solar systems, Trojan planets may exist as well, either as small rocky worlds accompanying gas giants or even in rare cases two Earth-sized planets sharing the same orbit around their star. Although none have been confirmed yet, the discovery of such a system would change many theories about planetary formation and stability. Future telescopes may eventually detect these unusual worlds. As scientific tools grow more powerful, the Trojans move from theoretical concepts to real destinations. Telescopes, such as the James Webb Space Telescope and upcoming ground-based observatories, can study their spectra with finer detail. These observations will help determine whether Trojan asteroids contain organics, hydrated minerals, or unusual chemical signatures. Each discovery adds another piece to a greater puzzle that stretches across billions of years. The Trojans form part of the solar system's hidden memory, storing records of processes that shaped everything from the sun's earliest winds to the formation of habitable planets. In a broader sense, Trojan Worlds remind us that the solar system is full of quiet companions traveling alongside us, even when we do not notice them. They highlight how much remains undiscovered in a system humans often assume is fully mapped. The reality is that every year brings new detections of small bodies in unexpected places. Many are faint and elusive, but they enrich our understanding of the solar neighborhood. They show that Earth does not journey through the void alone. Instead, it moves within a complex network of objects, large and small, ancient and dynamic. The future of Trojan exploration is promising. Over the coming decades, more probes will likely be designed to visit and even land on these bodies. Touchdown missions could provide definitive samples that reveal the exact isotopic fingerprints of their minerals, telling scientists whether they are related to meteorites or represent completely new categories of material. Robots could examine their internal structure, search for small moons or dust streams, and map surface geology with stunning precision. Such missions would transform Trojan worlds from distant dots of light into richly detailed landscapes with cliffs, craters, and boulders shaped by billions of years of cosmic history. Humanity's fascination with the unknown is powerful. It drives us to explore and to question, even when the answers lie far beyond our reach. The Trojan worlds may seem small compared to planets and moons, but their significance lies in what they represent. They are the survivors of an era when the solar system was chaotic and violent. They traveled through epochs of collisions, migrations of giant planets, and the slow stabilization of orbital paths. They endured long before life appeared on Earth, and they will remain long after our species has changed, grown, or moved on to other frontiers. In conclusion, Trojan asteroids stand as silent witnesses to the earliest chapters of the solar system. They hold the key to understanding how planets formed, how gravity shaped the architecture of celestial neighborhoods, and how small worlds can coexist in harmony with giants like Jupiter. They remind us that even in familiar orbits, mysteries persist. These orbit-sharing companions travel with us, unseen yet ever-present, offering insights into time, formation, stability, and the delicate balance that defines our place in the cosmos. As missions like Lucy reveal their secrets, the Trojan worlds will no longer be distant enigmas. They will become known, studied, and appreciated as essential components of the solar system's grand story. And so the journey ends, not with finality, but with an open door. Because every answer the Trojans provide will lead to new questions, new hypotheses, and new explorations. The asteroids that share our orbit will continue traveling the sun's timeless circle, forever carrying within them the echoes of creation. They have been our companions for billions of years, and now at last, we are beginning to understand who they are.